In this video, we are going to talk about two examples of conformal maps. This is actually part 2 of my 2 videos that talked about conformal maps. So the first one, we defined what a conformal map was and did a couple of examples to illustrate. In this video, we are going to talk about two particular conformal maps. The first are solutions to the Laplace equations, and the second are the Schwartz-Christoffel mapping functions. This is our overview slide, which will spend 5 minutes or less, and before we go through these two topics in more detail and with more examples. The first conformal maps we will look at are the solutions to the Laplace equations. The Laplace equation in two-dimensional Cartesian coordinates is the second order partial derivatives of a function phi of xy is set equal to 0. Then we can also use this del operator, which is the partial derivative operator, and since we're looking at second order, we put a del squared in front of the phi. If we have a function that is analytic, and we have a mapping function, which is the same thing. Remember, a function or a map is just going to go from one complex plane to another. So if we have a function, a mapping function that is analytic, then the functions u of xy and v of xy will satisfy a two-dimensional Laplace equation. In other words, u of xy, when we take the second order partial derivatives, we can denote it again with the del squared sign, will equal to 0. And the second order partial derivatives of v of xy, again denoted with the del squared sign, will equal 0. And because they satisfy Laplace's equations, either one can be interpreted, for example, as an electrostatic potential or as the pressure in a fluid flow problem. The second type of conformal map we will look at are Schwartz-Christoffel mapping functions, which uses conformal mapping techniques to design a mapping function from a particular set of boundary conditions. The mappings take this form here, and the significance of them is that they map the real w-axis into a set of straight line segments that may be closed to form a polygon in the finite z-plane. And because we can take a bunch of straight line segments and group them together, a variety of boundary shapes can be constructed. And to obtain w, we must integrate this dw dz, and then the function we get here, we must invert. The inverse of z of w will give us w of z. And this is what the general form of the Schwartz-Christoffel method gives us. Again, it's a straight line segment here, and then at z1, we have another line segment, possibly at a different angle, z2, another different angle, z3, another different angle, and we can keep going. Eventually, we can close this to form a polygon of any kind of shape. That covers our quick overview, so we'll take a closer look at Laplace's equations next. We will start with the Laplace equation, again, that takes this del squared, that's the second order partial derivatives of phi of xy, and set that equal to 0. I'm going to replace my phi with w, so I have a function w that takes an x and a y value, and it has a real part, u of xy, plus an imaginary part, v of xy, that gets multiplied by I. I'm going to assume that w is analytic. And we're going to be good with that because when we have this is from our summary page, we start with saying the mapping function is analytic. Because it is analytic, it should satisfy the Cauchy-Riemann conditions that the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y, and partial of u with respect to y is equal to negative partial of v with respect to x. Now, because these u and v satisfy the Cauchy-Riemann conditions, the partial derivatives are continuous, these partial derivatives here, so we can take the partial derivatives of these partial derivatives to get our second order partial derivatives. So this equation first, let's take the partial derivative of this left-hand side, and that'll give us d2 u of xy. I'm taking it with respect to x, and then with respect to x a second time. On this right-hand side, I'm going to take d2 v of xy. I have the partial derivative with respect to y here, and now I'm going to take with respect to x. So these are my partial derivatives with respect to x twice. And one thing to remember from vector calculus, it doesn't matter if you it doesn't matter if you take the partial derivative with x first and then the partial derivative of y, it'll be equal to taking the partial derivative of y and then the partial derivative of x. And a quick example, in case you've forgotten this from vector calculus, if we have a function f of x y equals 3x squared y cubed plus 4x cubed plus 2y squared, partial derivative of f with respect to x, so treating y as a constant, we get 6x y cubed and then our 12x squared. And now if we take the partial derivative of this with respect to y, in other words, that's d2f dx dy, with respect to y will give us 18xy squared. This goes away since it's not dependent on y. And now if we do partial derivative of with respect to y first, we're going to get our 9x squared y squared, this goes away, plus 4y. And then second we do partial derivative with respect to x of this, we get 18xy squared, which is the same thing. So it doesn't matter what order we put this in, which is why this kind of got swapped around. And then we do the same thing to this half over here. We have d2u dy squared, we're taking with respect to y, and here we have minus dv2v dy dx. I'm going to add these two u's together on the left-hand side of the equation, and on the right-hand side of the equation, I'm going to add the two v's together. This over here is just the second-order partial derivative of u with respect to x, second-order partial derivative with respect to y. In other words, it's just this over here. So I'm going to rewrite that as my del squared u of xy. And this is equal to 0. Now, why is that? Oh, we'll have to trace this back a little bit. Over here we have d2u with respect to x. Here we have d2u with respect to y. But d2u with respect to y is over here. Oops, I didn't really mean to circle it. But d2u with respect to y squared is equal to negative d2v dy dx, which is over here. But this is the negative of d2u with respect to x squared. So this here is the negative of this, so when you add them together, you'll get 0. We can do something similar for v, where we take the second-order partial derivatives, and we see that the Laplace equation with v of xy is equal to 0. So v satisfies Laplace's equation. I have that summed up over here, that u satisfies Laplace's equation, v satisfies Laplace's equation, and therefore, if a mapping function is analytic, the functions u of xy and v of xy satisfy a two-dimensional Laplace equation. And because of that, either one can be interpreted, for example, as an electrostatic potential or as the pressure in a fluid flow problem. We have our first example. In electrostatics, the electric potential satisfies the Laplace equation in a charge-free region, and conformal mapping functions can therefore be used to generate solutions to two additional electrostatic problems. So consider the function w equals z squared. This is analytic over here. So if the function's analytic, the real u of xy and the imaginary v of xy satisfy a two-dimensional Laplace. So the real part of wz is a solution to Laplace's equation and can be identified with an electrostatic potential function, which is phi of xy is equal to u of xy, which is equal to x squared minus y squared. This is the u function of w equals z squared. The two-dimensional surfaces of constant potential are given by x squared minus y squared equals a constant. I have my x squared minus y squared equals 5, x squared minus y squared equals 0, just, solving this one because it's the easier one. We get x squared equals y squared, x is equal to plus or minus y. So this is our phi equals 0. We have 1 here, 2, 3, 4, and 5 is this hyperbola. If plates were placed on x equals plus or minus y, that's for our solution for x equals 0, and at x squared minus y squared equals 5, this is this hyperbola here, and held at x squared minus y squared equals 0 and x squared minus y squared equals 5, electric potential in the space between these plates would be given by V is equal to x squared plus y squared. And here we have 1, 2, 3, 4, and then 5. Since field lines always run tangent to the field, if y equals y of x is a field line, then dy dx, that's the change in y with respect to x. In other words, e of y, the partial derivative with respect to y over partial derivative with respect to x, is equal to minus du xy over dy, and minus du of xy over dx. And by the Cauchy-Riemann, that means that's equal to minus dv xy dx, and then dv xy dy. Doing some algebra on this last equation, I can multiply both sides of the equation by this delta v dy. So over here I have my delta v of xy dy times my dy dx, and then I'm left with minus dv dx on the right hand side, and then multiplying, what did I multiply? Dx on both sides of the equation. So I have dy dv dy equals negative dv over dx times this other dx. If I move this over to the other side, so I'm going to add this to this over here, I'm going to have, well, I've moved this here, so dv dy times dy, that's over here, and then our partial with respect to v dx times dx, that's over here. This is just the total differential, the derivative of v of xy. And then since I had moved this over, added it to the other side, this right-hand side is 0 over here, meaning the total differential of the v of xy equals 0. So the field lines are lines of constant v of xy, right? Because when we take the derivative, we get 0. That must mean the field lines are constant. And the field lines are given by v of xy equals 2xy. I drew some field lines here, and to get the field lines, I just needed to make sure that every time they crossed one of these lines of constant potential, that it would cross perpendicularly. So if they aren't perpendicular, that's my limitations as an artist. They should cross perpendicularly. Our next topic is the Schwartz-Christoffel mapping function. It uses conformal mapping techniques to design a mapping function from a particular set of boundary conditions. And what I'm going to do for you is I'm not going to derive this mapping function here, which is our Schwartz-Christoffel mapping function, but I'm going to give it to you, and then I'm going to show you why it works. And what it will do for you is map the real w axis. So this is the z plane, so let's pretend like this is the w plane. So it'll map this real axis onto the z plane in this way into a set of straight line segments. So here's one line segment, a second line segment, third, and a fourth line segment. They may close to form a polygon in the finite z plane. And it's a set, so it can be, n, like many line segments. So you can get a variety of boundary shapes from this function here. So this is just a mapping function. And then once we establish that this is the equation that will give you this behavior, we're going to obtain w of z by integrating dz dw, and then after that we'll need to invert. So in our big picture, the first thing we're going to do is show that this Schwartz-Christoffel mapping function maps the real w-axis into a set of straight line segments that may close to form a polygon in the finite z-plane. Again, a mapping that takes the straight line, that is the w-axis, and maps it onto the polygon. We are going to start by taking a single factor, so just one of these factors, which is a, and we're going to start with the 0th. So instead of starting with 1, we're going to start with 0. So a w minus w naught raised to the minus k naught. And this is how z is changing with respect to w. So a is a complex number, w minus w naught are both complex numbers. That's what this c with a line, it's supposed to suggest a bold c. So these are all complex numbers. This also w minus w naught, a complex number minus a complex number is a complex number. And this k naught is our exponent, so it's a real number. We're going to use that technique from conformal mapping where we look to see how the grid lines or how the lines where either u or v are held constant map onto the z-plane. And we're going to start by asking, how does the line v equals 0 map onto the z-plane? And to answer this question, we're going to look at this in polar coordinates. So remember, a is a complex number, w minus w naught, that is also a complex number. So in polar notation, we're going to represent a with r e to the I theta, and then w minus w naught, that's also a complex number minus a complex number is a complex number. We're going to represent it with r prime e to the I theta prime, and this complex number is raised to the minus k naught. Algebraically, we do the multiplication. We can group the radiuses together, r prime. Then we'll have e to the I theta plus theta prime. Oh, and this theta prime also gets multiplied by the minus k naught. So we have theta minus k naught theta prime. Do you remember when we started chapter 6 and started talking about complex analysis? We talked about mappings, or we talked about functions of complex variables, and we talked about mappings. And there were 3 things that could happen, which were translations, rotations, reflections. What we're concerned about in this chapter are rotations. Remember that when you multiply a complex number z by another complex number, e to the I theta prime, what that ends up doing is it rotates the vector, right? This part here is how your radius of your vector, this is about your angle. So it rotates the vector counterclockwise by theta prime. And that's exactly what's happening here. Our original vector A is getting rotated by k naught theta prime in the clockwise direction. The negative indicates the negative orientation. We are going to use this bracket to denote the phase operator that generates the phase of a complex number. So looking at the equation, the little piece of our Schwartz-Christoffel mapping, the angle or the phase of dz dw is equal to the phase of A times w minus w naught raised to the k naught. And that phase over here is equal to the phase of A, that's our theta, minus k naught times the phase of theta prime. And remember, theta prime is the angle of w minus w naught, or the phase of w minus w naught. And I went ahead and labeled this, right? We had multiplied our A times our w minus w naught, and we got a new vector, a new complex number, with this radius r prime, and this angle here, this phase here, theta minus k naught theta prime. So this is the phase of A times w minus w naught to the minus k naught, right? This is the phase here. This part of the phase comes from the phase of A, and this part comes from the phase of w minus w naught, the theta prime. Next, we're going to consider the phase of dz dw as w moves from negative infinity to positive infinity along the real axis. So let's look at w minus w naught first. So remember, for w minus w naught, if you want to express the vector that goes from point A to B, so we're going like this, we're going from point A to B, then we express that as b minus a. That is your ending point minus your starting point. So here when we have w minus w naught, if w is to the left of w naught, as in this case, then, let's see, w is to the left of w naught, then our direction, w naught is our starting point. So the direction the direction of W minus W naught, which is what is over here in our formula, goes to the left. Whereas over here, if W is to the right of W naught, so our vector representing W minus W naught goes in the direction of positive infinity. Now looking at this, again, coming back when W is to the left of W naught, so the phase change, if we're going from negative infinity to infinity, so I'm looking at this, we're moving W from negative infinity to positive infinity. The phase change for W minus W naught is 180 degrees because it's going in the opposite direction. So in other words, 180 degrees is the same as pi radians. Over here, if we're going, again, from negative infinity to infinity, this W minus W naught is in the same direction, so there's no phase change. We're just continuing in the same direction, which means when we look at this portion of our formula over here, that dz dw, or the phase of dz dw, is equal to the phase of A minus k times pi now over here when W is to the left of W naught, and is equal to just the phase of A because this portion becomes 0 when W is to the right of W naught. I've summarized these points here. We have the first part of our Schwartz-Christoffel mapping, and then we have the phase of dz dw, which we have simplified to the phase of A minus k naught pi when W is to the left of W naught, and the phase of A when W is to the right of W naught. So now we're ready to look at this question: how does the V equals 0 line map onto the z plane? As W moves along the real axis, here we have the real axis and our W's moving along the real axis, the mapping function will generate a line in the z plane. As W is incremented by delta W, z will change by an amount delta z, which is equal to dz dw times delta w, and the phase of the delta w and delta z steps are related by phase of delta z, using this equation up here, is equal to the phase of dz dw plus the phase of delta w. Remember, because these are two complex numbers, dz dw and delta w, that means their angles add together. When we multiply two complex numbers, we add their angles together. Now as W moves to the right along the real axis, the phase change, or its angle with respect to the real axis, the phase change is equal to 0 because we're just moving along here. We're not, making any sort of angle with this real axis. So that then our phase change in delta z is the phase change in dz dw. Now, if we think of letting point W naught map to Z naught, so W naught here is in our UV plane, our W plane. When we map it, it comes over here in the XY plane as Z naught. So as W moves away from W naught, so we take these little incremental sections, delta W, we move to the right on the real axis, another delta W moving to the right, and a third delta W moving to the right. Theoretically, these are all the same. I should say these are all the same delta W, changes in W. Even though my drawing may be off a little bit, they are supposed to be the same. Then over here, what happens to delta Z is delta Z is changing. It's moving a little bit to the right. It's moving a little bit up. So we have an incremental change delta Z, and delta Z. So Z moves away from Z naught in steps of delta Z, and that's what we have here. And the result of the mapping of this part of the real W axis, the mapping of the real W axis here to here, is a series of delta W's are all at an angle of 0 and all the same length, that's delta W, are mapped to a series of delta Z's. The delta Z's are not necessarily the same length, but because the phase of W is the same, the delta Z's will all have the same phase, which is going to be the phase of A. And we get that, the phase of A, from over here, our previous result, that the phase of dz dw is equal to the phase of A when W is to the right of W naught. The mapping of the real W axis from negative infinity to W naught can be done in the same way, but now all the delta z's are at an angle equal to the phase of A minus K naught pi. And again, this comes from our previous result over here, that the phase of dz dw is the phase of A minus K naught pi when W is to the left of W naught. Consequently, and I put an asterisk next to this statement because this is a key point. So when we're mapping the function dz dw equals A, where A is a complex number, times W minus W naught, these are complex numbers, raised to the minus K naught, where K naught is a real number, maps the real W axis. At this point, we're talking not just about mapping from W naught to the right, we're talking about the entire real axis onto a line in the z-plane. Then that map will be made up of two straight line segments. Remember, at this point, we only have one factor here, which is our W naught and K naught, but there's then going to be two straight line segments because there's a break point at z naught. So in other words, as we're mapping, W's coming along here and we're mapping, we hit W naught, which corresponds to Z naught, all of a sudden we're going to change our angle by K naught pi. So we can look at this over here in the Z plane. So we're coming along at some angle, and the moment we hit Z naught, we change our angle by K naught pi. I cleared out some space here, but I summarized the key points that we've been talking about, and I'll go through it one more time. So consider our function W equals W of Z and its inverse, which is Z equals Z of W. And I have this equation for dz dw, which is this first factor here of the Schwartz-Christoffel. So we're only looking at the first factor, which is A, a complex number, times W minus W naught. Again, here, W and W naught are complex numbers, to the negative K naught, where K naught is a real number. It's an exponent. When we want to see how the phase changes now of this dz dw, we recalled that when we multiply this complex number by another complex number, W minus W naught, what happens to the phase is the angle of this complex number gets added to the angle of the second complex number it's being multiplied by. So in other words, the phase of dz dw is equal to the phase of A times W minus W naught to the negative K naught. I just copied this over. But now what this is, the phase of this product of two angles is the phase of the first angle minus, we can pull the K naught out, it's just a constant, the phase of the second angle we're multiplying by. So we have this formula here. We then looked to take a closer look at this formula here, and the first thing to remind you is if you want to express the vector from A to B, if you're going from point A to point B, the vector going from A to B is going to be the vector B minus A, your ending point minus your starting point. Over here, since we're looking at the vector W minus W naught, that means W minus W naught has this direction, and over here W naught is your starting point. So we're going to compare this W minus W naught to W as W moves from negative infinity to go this direction, right? We're going in the positive direction. Well, this W minus W naught is in the opposite direction, so our phase change has to be 180 degrees, 180 degrees, or in other words, it's going to be pi radians over here. And that's what we get here. So if W is to the left of W naught, then our phase change is going to be our phase of A minus K naught times our 180 degrees, or pi radians. Over here, when we're traveling from negative infinity to infinity, our W minus W naught vector is in the same direction, so we make no change here. So in our phase of dz dw, this term goes away, and we're left with the phase of A when W is to the right of W naught. Next, we asked, how does the line V equals 0 map to the z-plane? And the V equals 0, that's when the imaginary part is 0, which means we're on the real number line. I'm not sure why your book expressed it this way instead of just saying real number line, but anyway, what happens as we travel along the real W axis, then we're mapping along some line in the z plane, and then when we hit this point here, W naught, which maps to Z naught, we're going to have this phase change. According to our formula over here, our phase change is going to be K naught times pi. Continuing on, and at this point it gets a little easier, so don't worry too much. I'm not going to keep going at this pace. It's an easier pace now. These ideas can be extended to a mapping function whose derivative has this form, this Schwartz-Christoffel mapping form. dz dw is equal to a, w minus w1 to the minus k1, w minus w2 to the minus k2, up to w minus wn, k sub n. So instead of just one factor, we have, in this case, n factors. And our w, w1, wn, up to wn, they correspond to our different complex numbers, and they map over to our z1, z2, up to zn. And at each of those points, well, we also have, I should say, these k1, k2, k3, up to kn. So these, the n values of n are increasing, and they're arbitrary real numbers. And so what happens is, at each of these w1s, the corresponding z1 then will have a potential change in phase. This w2 then will have its corresponding z2 with another potential change in phase. Up to wn will have the corresponding zn with a potential change in phase. So the mapping function that has this form for its derivatives maps the real w-axis into connected straight line segments in the z-plane. In this case, there are n straight line segments. In this way, the derivative of the mapping function can be set up so the real w-axis can be mapped into an arbitrary shape made up of, in this case, n straight line segments. And this is the picture from the z-plane, the general form of a Schwartz-Christoffel mapping. So here we have z1, and then we have a change in angle, z2, another change in angle, z3, another change in angle. This last point outlines the two other things we need to do. Sorry, this is getting long. But currently, we have dz dw. And remember, what we wanted to find was the mapping function w of z. So the first thing we need to do is integrate dz dw in order to get z of w. Then once we have z of w, we need to find its inverse to get w of z. And remember, the value of the Schwartz-Christoffel method is the real w-axis can be mapped to a set of straight line segments that may close to form a polygon in the finite z-plane, and a variety of boundary shapes can be constructed. I am going to use this example here to show how we integrate and then invert to find our W function. Our example is to determine the electric potential and field around a sharp two-dimensional spike shown here. The spike and the ground plane are held at 0 volts, while the potential goes to infinity at an infinite distance above the ground plane. I've started by breaking this up, this spike, into a portion that comes before the spike where we are at 0. And then at the spike, I'm going to make a little peak going up. And I did make this distance more than 0 just because I wanted to show it. And then I have a peak going down. And then finally, we have our flat area again where we go back to 0. And this way, I can think of this spike as being some z1, and then at z1 we have a change where our phase changes, and then at the top at z2 we have another phase change where we come back down, and then over here at z3 we have a final phase change to give us the angle is equal to 0. So these points, Z1, Z2, Z3, are mapped to the points W1, W2, W3, all which lie on the real W axis. So as W moves along the real axis, Z moves along the path above, encountering Z1 first. And at Z1, there's a pi over 2 counterclockwise bend, right? So we go from here to up here. So our phase change is from 0 to pi over 2. And then which means that if this is pi over 2 and k, where is that? I don't have that formula. Okay, I pasted it here. Since our phase change is k times pi, then that means our k naught is equal to 1/2. We continue along our path. We're up here at Z2, but now we need to come back down. So this, instead of going up, we come back down. So it's a 180 turn. In other words, it's a minus pi radians turn, which means our K2 is going to be equal to -1. I should have kept that formula here, but K2 is -1. Then at this point, at Z3, we want to continue going along on our straight path. So from here to here, we just need to go 1/2 a radian. So K3 is 1/2. Which means now we have our formula for dz dw is equal to a w minus w1 to the minus 1/2, w minus w2 to the 1, w minus w3 to the minus 1/2. And I was just looking at this. Remember, our k, we make our exponent to the negative k. So negative, positive, and negative. At this point, a bit of trial and error is necessary to figure out the constants a, w1, w2, w3. Often I think of trial and error as like a bad thing because who wants to spend all their time? I mean, there's so many numbers to try. But for your homework, for your exam problems, I'm going to tell you, look at the geometry of the situation, which we will do in a minute, but also stick to small numbers and preferably integer numbers. I mean, if you really have to do maybe 1/2, but don't get into really complicated decimals and don't get into like huge integers either, small numbers. And whatever we choose now for W1, W2, W3, it needs to be consistent with our drawing here or our drawings here. And the idea is when we hit the first point Z1, we're on the real number line. And actually here, we're actually at 0. So Z of W1 needs to be equal to 0. At Z of W2, that's when we hit our next point. At this point, we're at I along the I axis. So let's choose I. And then when we come back down at z equals 3, we're going to be back down on the real axis at z equals 0. So again, we're choosing the easiest numbers such that we're on the real line, we're on the I-axis, we're on the real number line. For symmetry, we're going to try W2 equals 0, W3 equals negative W1, and we set W1 equals to 1 and W1 equals to -1, again, small numbers. And since A is a scaling factor, we're going to set A equal to 1, and if we need to rescale later, we'll just rescale. So with our proposed constants for A, W1, W2, W3, our equation becomes dz dw equals W minus W1 over, and that's this term here, because it doesn't have a negative exponent, then W minus W1 to the 1/2, and W minus W3 to the 1/2, which is equal to W2 is 0, W plus 1 to the 1/2, W minus 1 to the 1/2, which is equal to W2 over W squared minus 1 to the 1/2. And at this point, to make space, I just wrote our last line up here. So we have our dz dw is equal to W divided by W squared minus 1 to the 1/2. Now the next thing we need to do to get z rather than dz dw is integrate with respect to W. So here I have the integration dw, W over square root of W squared minus 1. So z is equal to c, some constant, times square root of W squared minus 1, which means now when I solve for W, remember we actually wanted W is equal to square root of z squared plus 1. So here is our mapping function that gives us this Christoffel mapping that we wanted in order to get this spike. We will do our quick check of our constants. Remember, we wanted z of w1 to equal to 0. So when we plug in -1 into over here, we're going to get 0. So that's good. Z of w2, where did we have that? Z of w2 should equal to I. So we're going to plug in z of w2, which is 0, plugging into here gives us the square root of -1, which is I, so that's good. And z of w3, where was z of w3? We want that to equal to 0, so z of w3 is equal to, what did we set w3 equal to? 1. So plugging in 1 over here, we get 0. So far so good. One last step for this example, we see that w equals square root of z squared plus 1. That is analytic everywhere except at z equals plus or minus I, which means this mapping function will generate a solution to Laplace's equation because it's analytic, and it will generate a solution to Laplace's equation everywhere except at z equals plus or minus I. And to obtain the solution, the functions u of x and v of xy must be determined. So when we have w equals square root of z squared plus 1, using w equals u plus iv and z equals x plus iy, we have z squared, which is u plus w squared. No, just, where is this? Oh, I'm going to square both sides of the equation. So w squared, which is u plus iv squared, plus z squared x plus iy squared plus 1. Solving algebraically, I get my new real part, x squared minus y squared plus 1, and my v as 2xy. I moved this up here to give us space, but you can see I didn't need a lot of space because we're almost done. This next part is all algebra. So first I solved for u using this equation here. So I get u equals xy over v. Now I plug in for u into this equation here, which I'll underline. And I'll get uy over v squared. I have my v squared. I move my x squared over, I move my y squared over, I move my y1 over, and I set that equal to 0. Well, because this equation, it ends up equaling 0 because nothing's left on the right-hand side. Some more algebra over here. We can then use this equation, x squared y squared minus v to the fourth minus x squared v squared plus y squared v squared minus v squared equals 0 to generate lines of constant v by setting v equal to a constant in the z-plane, which we will interpret as lines of constant potential. A computer is useful in making these plots, and this is generated in your book, so I'm not going to reproduce them here. And the electric field lines are determined by setting u of xy equals a constant, and the equation for these lines is obtained by eliminating v from the above equation here to get u to the fourth minus x squared y squared minus x squared u squared plus y squared u squared minus u squared equals 0. And again, examples of this is plotted in your book, so I am not going to reproduce them here. To review what we have covered in this video, this is part 2 about conformal maps, and there are 2 maps that we were particularly concerned with in this video. First is solutions to Laplace equations. The Laplace equation for 2-dimensional Cartesian geometry is given by the second order partial derivatives of a function phi of xy is equal to 0. So this is the Laplace equation. Often we use this del squared to denote the second order partial differential equations. So if a mapping function is analytic, then the functions u of xy and v of xy satisfy this Laplace equation. So here is what that means. So the second order partial derivatives of u of xy, which we can denote with the del squared, is equal to 0, and the second order partial derivatives of v of xy, which we can denote with the del squared, is equal to 0. And either one of these can be interpreted as an electrostatic potential or as pressure in a fluid flow problem. The second conformal map we were looking at is the Schwartz-Christoffel mapping function, and this is useful because we can map a real line w axis into a set of straight line segments that may close to form a polygon. So from a straight line axis, we can make any polygon, and then from there a variety of boundary shapes can be constructed. This is the mapping function we have. The mapping function is in terms of a derivative. dz dw is equal to a complex number a times w minus w1. Again, this is in the complex plane. These are complex numbers minus some integer exponent. W minus W2, this starts the second bend or second line segment, raised to the minus K2, and then our third line segment raised to the minus K3 up to Kn. Since this is a derivative, to get our function w, first we need to take the integral of this to get z, and then once we have z, we take the inverse to get w. So here, to obtain w, we must first integrate, and then we need to invert. So that's it for this video. Thank you for watching.